CD160021. Today, my group members and I will be presenting on polytropic process and work boundary of a closed system. So for me, my part would be about the ideal gas. So my topic is the ideal gas equation of state. As you can see, ideal gas is actually a hypothetical gas whose molecules occupy negligible space and have no interactions, and which consequently obeys the gas law exactly. Second, any equation that relates the pressure, temperature and specific volume of a substance is called an equation of state. Okay, the third point, the simplest and best known equation of state for substances in the phase is the ideal gas. The fourth part, this equation predicts the PVT behavior of a gas quite accurately within some properly selected region. The fifth part, the vapor gas of substance is customarily called a gas when it is above the critical temperature. So as you can see this picture, it is the basic picture of ideal gas. Ideal gas, and this is not ideal gas, this is how you can differentiate. If you see ideal gas, the particles are quite far apart, whereas for non-ideal gas, the particles are quite near. Okay, this is the ideal gas equation. PV equals to nRT. On the whole, this is an easy equation to remember and use. The problem lies almost entirely in the units. I'm assuming below that you are working in strict SI units. Okay, this is the picture for the equation derivation. As you can see, P is the pressure. The unit is in Pascal, whereas V is volume. N is the amount of substance in mole. R is ideal gas constant, whereas T is temperature. Okay, the gas R is different for each gas, if you can refer the figure, and it's determined from R equals to RU over M. The unit is kJ over kg or kilopascal, where RU is the universal gas constant and M is the molar mass, also called molecular weight of the gas. The constant RU is the same for all substances. Okay, as you can see, for air, the value is 0.280, helium is 2.0769, argon is 0.2881, whereas nitrogen is 0.2968. The molar mass, the unit is M, can simply be defined as the mass of 1 mole, also called a gram mole, abbreviate G mole, of a substance in grams, or the mass of K mole. When we say the molar mass of nitrogen is 28, it simply means that the mass of 1 kilomole nitrogen is 28 kg, or the mass of 1 bmol of nitrogen is 28 lbm. That is M equals 28 kg over K mole. So you can see these are the other equations. The mass of system is equal to the product of its molar mass M and the mole number N. M equals to Mn. The ideal gas equation can be written in different forms. For example, V equals to MV equals to PV equals to MRT. The second one would be MR equals to, in bracket Mn, R equals to NRU equals to PV NRUT. And the final one would be V equals to NV equals to PV equals to RUT. Okay. By writing the equations twice for a fixed mass and simplifying, the properties of an ideal gas at the two different states are related to each other. So the formula is P1V1 over T1 equals to P2V2 over T2. I have stated 2 videos there, we will see after this. So this is an example question of ideal gas. As you can see, the pressure in automobile tire depends on the temperature of the air in the tire. When the air temperature is at 25 degrees C, the pressure gauge reaches 210 kilopascal. If the volume of the tire is 0.025 meter cube, determine the pressure rise in the tire when the air temperature in the tire rises to 50 degrees C. Also, determine the amount of air that must be bleed off to restore pressure to its original value at this temperature. Assume the atmospheric pressure to be 100 kilopascal. So you can see this is the diagram, and the units are given. Volume is 0.025 meter, temperature is 25 degrees C, pressure is 210 kilopascal. Okay, so there's two assumptions for this question. The first would be air behaves as an ideal gas. The second one would be the volume of the tire remains constant. So from table A1, which is our, what table we call that? Okay, the table. Okay, from the table, we can refer the gas constant of air out equals to 0.287 kg or kg. I got it, actually it's the steam table. Okay, you can see the absolute pressure, the given formula for absolute pressure is P1 equals to Pg plus PATM. So, Pg given is 210 and the question stated there that atmospheric pressure is 100 kilopascal. You add in both, the total is 310 kilopascals. Okay, so for the final pressure, we use the formula given as I stated just now. P1 V1 over T1 equals to P2 V2 over T2. So you just change the formula and you get the value 3 over Tk divided by 208K multiplied with 210 kilopascals and you get 336 kilopascals. So now we want to find the pressure in tire. We use the formula P equals to P2 minus P1. So the value for P2 is 336. The value of P1 is 310. You get 26 kilopascal. Okay, for the part B, the amount of air that needs to be bleed off to restore the pressure. Okay, so for M1, we use the formula P1 over V over RT over 1 equals to 300. P1 value is 310 kilopascals, whereas V is 0.025 BTQ, as stated in the question above. You divide with 0.287 kg over kg, multiply with 298 K, whereas and you get the answer 0.0906 kilogram. Whereas for M2, P2 V2 over RT2, we follow the same steps as M1. So for P1, P2 we put 310 kilopascal, the same volume, divide with 0.287 over 323, and we get the answer 0.0836 kg. So the change in the mass of air is given as M equals to M1 minus M2 equals to 0.0906 minus 0.0836 equals to 0.070 kg. The two videos will be played after this. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Lukman Shakir Ramli. My metric number is AD150101. So I will present you guys about polytropic process for general substance and ideal gas, and that is my name there, Lukman Shakir. Okay, what is before this? We have learned from our previous presenter, which is Arvin. He explained to you guys what is a polytropic process. So I want to ask you guys, do you remember what is a polytropic process? So don't pening-pening, I will explain to you guys what is polytropic process. So polytropic process is describing any reversible process which is open or closed system of gas or vapor, which this process involves both heat and work transfer. Good. Okay. And this polytropic process must obey a certain law, and this law will materialize in a form of equation which is the pressure, volume, and the polytropic index, which is N, must equal to constant. And here guys, you can see this equation, which is P, which is pressure, V, which is volume, and N there is a polytropic index equal to C, which is constant. Okay, polytropic process as a general substance. So in order to understand this, you guys must remember the equation, which is PVN equal to C, and this in order to understand polytropic process for general substance, we will allocate certain number to the polytropic index. For example, here we put N equal to 0, and after we put the N equal to 0, we can see the V is equal to the power of 0, and that is equal to 1, and then we got the equation pressure equal equal to C, which is pressure constant, and this equation is applied to the process with a constant pressure, which is isobaric process. Okay, next. And if we apply 1 equal to the value of n, then V will have the power to 1, and then we have the pressure PV equal to C constant, and then we say that this process has a constant temperature which is known as an isothermal process. And if we put n equal to infinity, then the V will have the power of infinity equal to C, and then the final equation will go to the volume equal to C, which is the volume is constant, and we know what process make the volume is constant is isochoric process. And if you guys is confusing about how did I get V equal to C, don't worry, I will explain to you guys in the next slides. And please don't forget this equation, very important. And here, how did I get the V equal to C constant? Here, when we put the V equal to V to the power to the infinity, we put the pressure also 1 over infinity, because we want to cancel out the power of the infinity. And then we can, when we put the 1 over infinity, we have to put also to the V. And after that, we can see that 1 over infinity is equal to 0. So pressure to the power of 0, and we know pressure to the power of 0 is 1. And because at the V equation, we can see the infinity power itself cancel it out, and we got the V to the power of 1. And then the final equation, V equal to the C, and that's how we got volume is constant, which is isochoric process. Okay. This chapter is a little bit hard to understand, so I hope you guys pay very detailed attention to the slides. So this slide is about polytropic process for idle gas. So what is idle gas? Idle gas is a term for what? A term for gas which is ideal. And go. So for those who doesn't remember what idle gas is, so this idle gas is represented by this equation, which is PV equal to mRT, where P is the pressure, V is the volume of the gas, while M is the mass of the gas, while R is the specific constant for the idle gas, and T is the temperature. And this, like I said before, polytropic process, I hope you can remember it, which is PVN equal to C, which is constant. So, how do we relate these two equations, which is PV equal to mRT with PVN equal to C? So how do we relate polytropic process for an idle gas? So, do you guys have any idea how to do this? Fine, I'll show it to you guys. Okay, before this, take a deep breath, because this will involve a lot of equations, derivations, and I hope you guys will stay with me to the end, so I might get you guys to understand what is this all about. So, okay, here we have the P1. 1 is represent a first state, and while 2 represent a final state. So before, what is this equation about? This equation is about an idle gas, which is PV equal to mRT, and this P1, V1 over mRT1 equal to P2, V2 over mRT2. So this is equations which involve a final process which and initial process. So after we have these equations, these four idle gas equations, then because of this process occur in a closed system, so we don't have to worry about the mass, because the mass will stay constant from the initial phase to the final phase, and also to the specific ideal gas constant R. So these two variables will stay constant throughout the process. So after that, because we know that about this two variables is constant, so we can eliminate these two variables and make the equation more simpler, which we will have P1 V1 over T1 equal to P2 V2 equal to T2. Okay. And then we rearrange the equations to get a ratio of temperature to the ratio of pressure and volume of the ideal gas, and we have the equations T2 over T1 equal to P2 V2 over P1 and V1. Okay, because this ideal gas is in a polytropic process, so we have to relate these two equations that I mentioned before this, PV equal to MRT and the PVN equal to constant. So how do we relate these two equations? So because we know that the polytropic process PVN equal to constant, so we have two phases of process, which is the initial one and the final one. So we put that P1 V1 and N equal to P2 V2 equal to N. So how do we put the equation for polytropic process into the ideal gas equations? So here we have it. When we first we need to rearrange the equation for this polytropic process itself, where we have this P2 over P1 equal to V1 over V2 to the power of polytropic index. And after this, you can see that there is a similar equation which we can find at the ideal gas, where we can substitute P2 over P1 into the ideal gas equation. So if you guys didn't see it, it's in this section, and then we have this section. If I second, so here we have the final equations. Oh man, I'm sorry, my mistake, a technical mistake. This is a very same equation, okay? So this is my mistake. I'm so sorry about that. Back to the mistake that I made here. So these two equations is the same. So I hope you guys understand what I talked about. So to the next slides. So we continue the equation before this, and we substitute the equation that we have before this into the ideal gas equation, and we have that equation, which what this equation tells us about is the ratio of the temperature equal to the ratio of the volume, and which is temperature 2 over temperature 1 equal to V1 over V2 to the power of N multiplied with V2 over V1. So in this process, we want to make the equations more simpler, so we don't need much time or longer time to memorize. So what we can do is we can look at the equation where we can find the volume V2 over V1, so that we can exchange the V1 equal to the V2 to the power of -1. So we replicate the equation. So next equation. So there you have it, where we have we change the V2 over V1 to the V1 over V2. When we have done this, so we can get the next equation, which is a much more simpler equation, which is T2 over T1 equal to V1 over V2 to the power of polytropic index -1, which is N -1. There, I hope you guys understand. And this equation tells us about the ratio of the temperature to equal to the ratio of the volume. So if you guys have the polytropic index and we have the initial temperature and initial volume, so you guys can get from the problem which you can face whether you guys want to find V1, T1 or T2. So after this, we can have another next equation, which is here. I hope you can understand. Which is the relationship. This equation we got from the polytropic process equations, and we rearrange that equation to these equations. So after this, and then after that, we have the final equations, which is this equation here, which is the ratio of the temperature to the ratio of the pressure. So from this we can find from any problem that we face, which need us to find the temperature at the final or initial, or the pressure at the final phase or initial phase. So we can use this equation to find that value. But however, we must have a certain value, which is T, and also the polytropic index. And what we can conclude from this is that from this all equation that we have see here, that we derive here, so we can see that the ideal gas equation at the polytropic process. So we can find the temperature, the pressure of the gas, and also the volume of the gas, where we can use these equations to find those values. Okay, I hope you guys understand. If you guys need more time to understand, I will provide you guys a video with a duration about 5 minutes there, and I hope you guys will have much more concrete understanding about this derivation for the ideal gas in a polytropic process. Thank you.
Let's sort out how polytropic processes work with ideal gases. So, we're given an ideal gas. I have to apologize, the drawings for this video aren't that engaging. It's a big parcel of gas. And we know for that there are 4 different versions of the ideal gas law. I'm just going to pick one. How about P big V equals mRT, where if you recall, P is the pressure, V is the total volume, M is the total mass, R is the specific gas constant for this ideal gas, and T is the temperature. And this is a polytropic process, so we know how those work. It's PV to the N equals constant. So let's combine these, and the goal here is to come up with a relationship between the temperature and either the pressure or the volume ratio. We already know the relationship between the pressure and the volume for a polytropic process, but since we have an ideal gas, we can tie in the temperature too, which of course may be useful. Temperature is a directly measurable quantity. Okay, so we'll start with the ideal gas law, PV equals mRT. And what I'm going to do is take a ratio for each of the initial and final states. So if you think about it, if PV equals mRT, it must be true that PV divided by mRT is equal to 1, and that has to be true both at the initial state and the final state. So we can say that that ratio, PV over mRT, must equal the same value for the initial case on the left, subscripted with 1, and the final case subscripted with 2 on the right-hand side of that equation. So we're setting up a ratio problem. The nice thing about this is that we're dealing with ideal gas, and it's implied to be a closed system, so we're not worried about losing mass. We're certainly not changing its composition. That means that M and R are the same on both sides. We don't need to subscript them, and so we can cancel those out. So we get that the ratio PV over T is constant for the initial and final state. Okay, let's solve for the temperature ratio. So T2 over T1 becomes P2 V2 divided by P1 V1. Okay, we'll move that up and keep that. Now we're going to use the fact that we have a polytropic process. So far that actually hasn't come up, but now we need to use it. So we know that the relationship is that PV to the N equals constant. That's true in the initial and final states as well as any point in between for a polytropic process. Well, we can rearrange this to solve for P2 over P1. So let's do that. P2 over P1 becomes the volume ratio V1 over V2 now raised to the nth power. You can convince yourself of that from the polytropic process equation. So our goal now will be to take this expression and plug it in up here so that we have temperature in terms of volume exclusively for an ideal gas polytropic process. Okay, let's do that. So we plug that in and we get that T2 over T1 is now this combination of volumes, but we're working exclusively in terms of initial and final volume and the polytropic index N. So that second part, V2 over V1, we can write as the reciprocal of V1 over V2. Normally that would be a weird choice, but the idea is to combine the arguments, so we want V1 over V2 to some power, and indeed we can rewrite that as T2 over T1 equals the quantity V1 over V2 to the n minus 1 power. Okay, so that's our first relationship between temperatures and volumes for a polytropic ideal gas process. Pretty straightforward. So if you can measure volumes, you can get temperature. Likewise, you can work backwards. If you measure the temperature ratio, you can get the volume ratio. And you don't even need numbers, you just need ratios. Let's come up with a similar expression for the pressures and temperatures. So we can start back with this, which comes directly from the polytropic process relation. So you can work out the relationship between V and P in terms of V1 over V2. And now we can just substitute this in, right? We just solved for V1 over V2. We can combine that with the top expression that we just derived and say that T2 over T1 must now be P2 over P1 quantity raised to the n minus 1 divided by n power. So if you know the polytropic index, and again you need something like initial and final pressures or initial and final volumes, you can immediately go through and get the temperature ratio for that process. That's a convenient aspect of an ideal gas.
Assalamualaikum warahmatullahi wabarakatuh. My name is Abdul Harun, AD150282. So for today I would like to explain about what is the polytropic process. The term of polytropic itself was coined originally describes the reversible process of gas, which is including closed and open system itself, which is involving the gas. Alright. So which is this process that involves both of heat transfer and work transfer, right? So a polytropic process is a thermodynamic process that obeys the relation where P is the pressure, V is the volume, V is a specific volume, and N is a polytropic index. Alright, and C is remain constant. This is the definition of a polytropic process, which is will be explained in sort of this equation itself. So the definition of polytropic process, which is for the first one, is including P2 and P1, and is equal to V1 over V2, which is including the power of N, which is N. What we call that? N is the polytropic index. Right. So for the fluid in an ideal gas, which is P2 over P1 is equal to V1 over V2, which is the power of polytropic index, and is equal to MRT1 P1 over MRT2 P2. Right. And the third one is the lead to two additional relationship for ideal gas, which is T2 over T1 is equal to P2 over T1, which is in the power of polytropic process minus 1 over polytropic index, and the another one is about the same. This is the illustration of polytropic process, which is the final condition that will show in this figure. P1 V1 with the power of polytropic index is equal to P2 V2 power of polytropic index. So this is the PV diagram for the polytropic process itself. Alright. So this basically I will literally explain about what is isothermal, isobaric, and isochloric cycle. Right. So for the term isothermal process, which is we can hear that the thermal term, which is we know that the temperature T will remain constant. Isobaric process, which is the process that the pressure will remain constant, and isochloric process is process which is the volume will remain constant. And the second is the process during which is the initial and final states are identical. Right. For isothermal process, which is the thermodynamic process, which is the temperature in the system will remain constant. Okay. During an isothermal process, there is a change in the internal energy, heat transfer, and also the work. Even though the temperature will remain the same. Alright. Something in the system work to maintain the equal temperature. So as a result, the gas which is in the cylinder will expand and push the piston outward. So by that we will get the graph, the PV diagram that as shown as the video, the animation. Isothermal process, meaning a very evaporation of water into the air is 1. As is the boiling of water in a specific boiling point, and we can also relate to the melting point of the ice. Alright. So this is the graph, which is PV diagram that tell us about the isothermal process. So throughout this graph, the temperature will remain constant, and there is a change in pressure and volume. Okay. So for the next one is example of isothermal process, which is in our real life. For the first one is in the refrigerator. So as we know, the refrigerator, the temperature in the refrigerator will remain constant. As the time being, the temperature will remain constant. And also the ice, as we can know, the melting point of the ice, which is at a certain temperature, the ice will melt, and the temperature is constant, but the solid state of ice will slowly become liquid state, which is we know the volume and the pressure will change. Okay, so the last one is the heat pump, which is the heat will remain constant, and also it can produce the heat with the constant temperature. Alright. Okay, so this is the illustration of isothermal process, as we can see from this figure. So this is the temperature. As we can see, the temperature is remain constant, and the graph of PV diagram is inversely proportional to each other. Okay, so this is the figure of isothermal process. As we can see, the volume and the pressure change while the temperature is remain the same. Okay, thank you.
Isothermal and adiabatic process. Isothermal process. In this process, temperature of the system remains constant. For a given number of moles of an ideal gas, we have PV is equal to nRT, where N is equal to number of moles, T is equal to temperature of gas, R is equal to universal gas constant. Since T is constant, therefore PV is also constant. The essential condition of isothermal process are: temperature should remain constant. Changes must take place at a slow rate. Specific heat of the gas is infinite. Adiabatic process. In this process, there is no exchange of heat between the system and the surroundings. Delta Q is equal to 0. The essential conditions of adiabatic process are: there should be no transfer of heat energy. Changes must take place at very fast rate. Specific heat is 0. The pressure volume curves of an ideal gas show two adiabatic process connecting two isotherms.
Okay, now we jump to this slide, the figure of isochloric process, which is we know that the temperature will increase and the volume will remain constant. As we can see, the cylinder didn't move a bit. Okay, so as this color will represent the pressure, which is the increase in pressure while the temperature is increased. Okay, so I have a question to ask. To my students. So what is the differences between? I want to ask to my student, what is the differences between isochloric process and isothermal process? Anyone can answer this question? Anyone? Raise up your hand. Okay, Nuzah.
I think I know. Isochloric is the pressure is constant, but the isothermal is the temperature is constant. Is it?
Do you think so, Shakir?
For my opinion, I think it is not correct, because as we can see from the diagram there, the volume is the one that is constant for isochloric. For isothermal, the temperature is the one is constant.
Ya, aku cakap apa ni salah?
Sir, I don't understand. Can you please explain more about that diagram? PV and what is that line represent? But I don't understand with the diagram.
Okay, so for increase up your understanding about this illustration and this figure, so I will play the video game. Okay, so as we can see, this is the candle that represent the temperature, which is we can say that the temperature is constant. So as we can see this cylinder, and there's a piston about that. So as the time being, for the temperature remain constant, but the volume increase. While the volume increase, the pressure also drop, as we can see from this graph. So when the temperature is constant, the pressure is drop and the volume is increasing up. So that's why we can produce this kind of PV diagram graph.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Zahan Biasan. I will proceed about the isobaric and isochoric. Okay, basically the isobaric is a process that the one where the pressure of the system, usually gas, stay constant. Iso means the same, but the varic means the pressure. Okay, pressure is related to the amount of force that the molecule apply to the walls of the container. Okay, let's say, imagine that you have a gas inside the movable piston and you heat up the gas. So by heating the gas up, you will make the molecule move faster, which will normally increase the pressure, but at the same time, you will know that the molecule at the same time, the piston expands, so increasing the volume and giving the molecule more room to move. Okay, since the wall of the container are now bigger, so the pressure can stay the same even though the molecule are move faster. That makes it an isobaric process. Okay. This is the PV diagram. As you can see, the pressure is remain constant, but the volume have a value, which is the VA and VB. So to summarize the volume, you can minus the value of VP minus VA. Okay. For more details, you can see the simple video about the isobaric. As you can see, this is the isobaric PV diagram and also the piston that I already explained. Okay, when the piston is heat up, so the pressure remain constant, but there's the increase of the volume. Okay, next I will explain about the isochoric. Isochoric process is the one where the volume of the system stay constant. Okay, what is the meaning of iso and what is the meaning of choric? Iso is same and choric means volume, so same volume. Okay, volume is the amount of space the material takes up. So this would be like heating a gas in a solid, which is non-expandable container. The molecule will move faster and the pressure will increase, but the size of the container stay same. Okay. This is the example of the PV diagram. Okay, as you can see, the battery is low. Okay, this is the example of the PV diagram. Okay, as you can see, there's the pressure and here's the volume. Okay, this the value of the pressure where the volume is constant. So, there's the P2 and P1. So to get the value is P2, P1 minus P2. Okay, for more understanding, let's see the simple video about the isochoric. this is the isochoric process. As what you can see is this is the piston, and when the piston is heat up, so the value of pressure is increased, but the volume is still constant. So this is the isochoric. Okay, as a summary, what we have already learned in chapter 2 is about the constant pressure, is constant volume, isothermal, and also the polytropic. So let's summarize this topic. Okay, the relationship between the P, V, and T. So for the constant pressure, P is constant, but for the volume, for the summary of this chapter, okay. For the chapter 2, what we can summarize is about the process. The process inside this chapter is about the constant pressure, constant volume, isothermal, and also the polytropic. Okay, the relationship about the P, V, and T is for the constant pressure, also the P is constant. So the formula is V1 over T1 equal to V2 over T2. Okay, for the work, the formula is P times the V2 minus V1. Okay, for the internal energy change, delta U, which is the mCV T2 minus T1. And for the heat, Q, mCP times the T2 minus T1. Okay, for the constant volume, the volume is constant, while the relationship for the P, V, and T is the P1 over T1 equal to P2 over T2. Okay, work is 0 because there's no work inside the constant volume process. Okay, for the internal energy change, the formula is mCV times T2 minus T1. Okay, for the heat Q, that's the 2 formula, which is the Q equal to U2 minus U1. Okay, if we integrate ini apa? Integrate dia kan? Mana? Macam mana boleh dapat U2 minus U1? Dia bukan dua formula ni, dia integrate kan? Dia bakal Kan Yang ni Yang mana? Yang ni Q itu U2 minus U1. Yang bawah ni P formula daripada atas kan?
Tu kan integrate kan?
Integrate
Dia U tu sama dengan mCV T2 tu kan?
U2 sama dengan
mCV T2. Kalau U1 sama dengan mCV T1.
Kalau yang ini work is equal to
PV
delta 1 P1
V
rho 1 V1
ln V2 V1 over V1.
Sebenarnya ln 1 V apa ni rho 1 V1 ln V2 equal to ln 1 time.
No one.
Kita boleh dapat yang ln V2 minus V1 ni.
Ada ni kot. Ada power.
Tak bro.
Baca je lah
Baca dah.
Saya. Okey, baca balik. Kita dengan drop.
Baca balik.
Apa?
Okay, for the heat, U is equal to the mCV T2 equal to mCV T1. So for this formula, U2 minus U1, so the original formula will be the Q equal to so the equation is Q equal to mCV T2 minus T1. The upside there is the original equation. So for the isothermal, the relationship between the rho V and T is T is equal to C. So P1 V1 equal to P2 V2. For the work, rho 1 V1 ln V2 over V1. So for the internal energy change is 0. So for the Q equal to W, and also the Q equal to ρ1 V1 ln V2 over V1. Okay, for the last process, which is the polytropic, the relationship between the PV and T is PV equal to constant. So this is the formula. T2 over T1 equal to V1 over V2 n minus 1. So P and also the P2 over P1 equal to T2 over T1 n over n minus 1. For the work is the P1 V1 minus P2 V2 over n minus 1, and the internal energy is NCV times T2 minus T1, and the last one is the heat Q equal to W plus U2 minus U1. Okay, that's all from us. Thank you for watching.
Mr. Anderson, and this is AP Physics Essentials video 85. It's on thermodynamics and PV diagrams, or pressure volume diagrams. And this is a picture of a fire piston. You can put some tinder, like cotton, in the bottom of a fire piston. You can slam your hand down on it, and since heat doesn't have time to escape from that piston, we heat it up and the thing starts on fire. And natives have known this for a long time. This is a native fire starter. You put some tinder on the inside, you slam it down, and then it starts a fire. And so a part of the conservation of energy is the first law of thermodynamics. Energy can neither be created nor destroyed. But we're going to study how this applies in a typical idealized gas, in a piston like this. And so our equation is delta U, so that's the change in internal energy, is equal to Q plus W. Q is going to be heat and W is going to be work. And so we can add energy to this system, this internal energy, by heating it up, or we can apply a force over a given distance to it. We can do work on it. And so what we're looking at is how energy can be transferred from the surroundings into the system and back again. Now we're not going to lose any energy. Remember, the energy is going to be conserved. And a good way to measure this using a piston is to graph the pressure and the volume over time. And so we're going to start with the piston kind of relaxed, and we're going to have a really high volume. So we've got a large volume here, but it's going to be a relatively low pressure. And then I'm going to compress that piston. So the surroundings are going to do work on the system. And as they do that, you can see we have an increase in the pressure inside. Now we did it slow enough that we're allowing that temperature to stay constant throughout that whole process. And so what's neat about a pressure volume diagram is the area under that curve is going to be the amount of work that we do. Now a common mistake in physics is to figure out who's doing the work. Is it the system or is it the surroundings? And so in any piston like this, the area under the curve is the work being done by the gas. And so you can see that we're going from right to left, and so this is negative work. And so what's work being done by the gas? It's negative work. Well, if it's negative work of the gas, that means it's positive work of the surroundings. We're adding work on the system, and so we're increasing the amount of internal energy on the inside. This would be an isothermal process since we're keeping this temperature the same. Now in physics 1 and 2, you don't have to do calculations, you just have to know qualitatively what's going on. But we could have a different process that we'll model here. It could be isovolumetric. We could lock the volume of that piston, and we could just add energy through heat. We could have isobaric when we keep the pressure the same, or in the fire piston we can do adiabatic cooling or heating. So that's when we're doing it so quickly that we're not allowing heat to kind of move in and out. And so let's start with a little simulation here. This is a PHET simulation. We've got the gas molecules on the inside. We can add heat right here, and then we can push back and forth on the piston on this side so we can do work. We can apply a force for a given distance. And so let's watch what happens when we run the simulation. The energy is in the molecules on the inside. What happens as I add temperature to it? I'm increasing their speed, and so I'm increasing their energy. Energy of the system increases. If I cool it down, energy of the system decreases. How else could I add energy? Remember, it's W, it's work. So we could push in on it. What's happening to the pressure and therefore the energy on the inside? It's increasing, and now that total internal energy is decreasing over time. And so it's nice to be able to use a simulation, but the two things that we can measure are the volume and the pressure. And so if we just keep track of the volume and the pressure over time, we can figure out what kind of a process is going on. And so this is a PV diagram. And so let's start with an isobaric process. In an isobaric process, we're going to keep the pressure the same, but we're going to be able to change the volume over time. And so a way to do that is allow this piston to move in and out. And so we can change the temperature. What's going to stay the same? It's going to be the same pressure on the inside. So that piston's going to move back and forth, but we can add energy into the system or we can pull energy out. Since it's free to move, the pressure is going to stay the same. And so if you see on a PV diagram this horizontal line, then you know it's isobaric. What else could we do? We could do isovolumetric. What does that mean? We're going to keep the volume the same. You can see the volume is always the same, so it's just going to move back and forth on here. We're going to increase or decrease the pressure. And so what would that look like? Using our piston, we're going to lock it in place. Now we can add temperature, we could pull that temperature out. We could also have isothermal. Isothermal is always going to look a curve like this. This would be an isothermal curve. And so how do we do that with a piston? Well, we'll use something like a heat sink where we can keep the same temperature throughout that whole process. And then finally we could do adiabatic. That's where we either pull it out or move it in really, really quickly and so fast that we can't lose temperature to the surroundings, and you're going to get a curve that looks something like that. Okay, so let's kind of model those using this PHET simulation. And so let me kind of get this thing going. There we go. And so now what we're going to do is we're going to keep the volume constant. So we've locked it in place. How are we going to get energy into the system? We could add heat. As we add heat, we increase temperature, pressure is going to go up. Let's say we add ice on the bottom. We're going to pull energy out of it. Heat's going to flow from the system to the surroundings, and the pressure is going to decrease. What's staying the same that whole time? The volume is going to stay the same. For the second one, let's keep the temperature constant now. So we've got a constant temperature. So you can see that I can't even change my heat controls here. So how am I going to get energy into or out of the system? It has to be through work. So if I apply a force from the outside, what's happening to the pressure on the inside? It's going up. If I do negative work from the outside, what's going to happen to the pressure? Pressure is going to drop off. And so we're going to get that nice curve on a PV diagram. And then finally, we can look at an isobaric process. In an isobaric, we're going to keep that pressure the same. What does that mean? This piston can simply move back and forth. It's going to be the same pressure exerted by the gas. If we cool it down, those molecules move slower. The piston's simply going to move in. If we were to add temperature to it, as we increase temperature, that we're adding temperature or heat into the system, what's going to happen? Those molecules are going to move quickly, but since the pressure remains the same, the piston's going to move out. And so what would the PV diagram look like in an isobaric process? Since that piston can move back and forth, the pressure is always going to remain the same. And so the volume is going to change over time. And so remember, the area under a pressure volume diagram is going to be the amount of work that we do. And so since we are taking a large volume and moving to a small volume, the work is going to be in that direction. And so we'd be doing negative work. Now remember, that's negative work of the gas itself, what's inside the piston. So what's the positive work? That's from outside. So that's going to be the work of the surroundings. And so did you learn to figure out how internal energy in a system can change? It's really only two things. We could add heat or Q, or we could do work. Do you know, looking at a PV diagram, which of the 3 or 4 processes this is? So this would be isobaric, this would be isovolumetric, this would be isothermal, and this is going to be adiabatic. And then finally, could you find the area under the curve? And if you know the area under the curve, could you figure out how much work is being done by the gas? Because that's going to be what's under the curve. I hope so, and I hope that was helpful.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Mukhtar. I want to present to you about the relationship of work boundary and PV diagram. Okay. What is the relation between work boundary equation and the PV diagram? So this is the diagram for the closed system. This boundary is moving boundary. So if we fill the container with a gas and we close it with the moving boundary, we will get this equation: delta WB equal to F force differentiate of S equal to PA pressure times area this is the equation for F. So dx, differential of S equal to P dV. dV we get from A multiply with ds. So we get dV. The differentiation of V, volume. So the area that we use in here is the area of the moving boundary. So the P is the pressure of gas, and ds, the delta, and the differentiation of S is the moving boundary from the initial point to the final point. Okay. Next.
The mathematical expression for the first law of thermodynamics, or the energy equation, includes a term which accounts for any work performed on or by the system during a process. One common form of work done in piston-cylinder devices is called moving boundary work, or simply boundary work. Consider a cylindrical vessel containing a fixed amount of some substance. A piston is placed in the cylinder on top of the substance. Let's take the substance as our system. Moving boundary work occurs when the boundary of the system moves as the substance is expanded or compressed. We will now derive a mathematical expression which we can use to calculate boundary work. Consider the gas enclosed in the piston-cylinder device. The gas has an initial pressure P and a total volume V. The gas expands and the piston is allowed to move a differential distance ds. The differential boundary work done during this process is equal to the force on the piston times the distance the piston is moved. The force acting against the piston is equal to the pressure of the gas times the cross-sectional area of the piston. The product of this area and the distance the piston moves is equal to the differential change in the total volume of the gas. The total boundary work done as the piston moves from point 1 to point 2 can be obtained by adding all of the differential work from state 1 to state 2. This is done by integration. Recall that work is a path function, so the integral of the differential boundary work done from point 1 to point 2 is simply equal to the total boundary work done during the process. In order to integrate the right side of the equation, we need to have a functional relationship between the pressure and the volume. In other words, we need to know how the pressure changes as the volume changes. This functional relationship can be seen by plotting the pressure as a function of the volume. Let's look at some examples of different process paths on the PV diagram. Suppose that the initial pressure is P1 and the initial volume is V1. The simplest case occurs when the pressure stays constant as the volume changes. In this case, the process path is simply a straight line from the initial volume to the final volume. Because the pressure is constant, it can come out of the integral. Evaluating the integral tells us that the boundary work done during this process is simply equal to the pressure times the change in the volume. Note that the boundary work is equal to the area under the process path on the PV diagram. Now, let's look at a different case where the gas behaves as an ideal gas and the temperature of the gas remains constant during the expansion process. The ideal gas law provides the functional relationship between pressure and volume. This relationship can be shown as a process path on the PV diagram. The mass of the system, the gas constant, and the temperature all remain constant during the expansion process, so they can come out of the integral. Evaluating the integral provides us with an equation for the total boundary work performed during the process. Again, the boundary work is equal to the area under the process path curve on the PV diagram. It's important to note that the equation we derived for moving boundary work is for a quasi-equilibrium process. This means that the system remains nearly in equilibrium at all times. In other words, the process is sufficiently slow that the properties in one part of the system do not change any faster than those in other parts of the system. For example, the entire substance in the piston-cylinder device is at the same pressure at any given time. A quasi-equilibrium process is an idealized process which can serve as a standard to which actual processes can be compared.
Okay, we continue. This is the area. The area of the under the graph of the PV diagram. Area equal to 1 to 2 dA. This is the process from 1 to 2. So we also can use this the integration of P dV. So WB is equal to the integration of P dV. So that means the area under the graph of PV diagram is the work boundary itself. So the relationship between the work boundary and PV diagram is work boundary is the area under the graph. For example, this is isochloric process. In isochloric process, when volume constant, this will be straight line. So there was no area under the graph. So this work boundary is equal is equal to 0. There is no boundary. So next, when pressure is constant, this is isobaric process. So when equation the pressure is constant, so there will be area under the graph and there will be work boundary. Next is the isothermal process. The isothermal process is giving area under the graph. So the area under the graph is WB. So there will be an area under the graph for isothermal process. Next, this is the key point for when we want to remember our process is isobaric. This bar is related with the pressure, so the pressure is constant. So when isothermal process, we want to remember, we remember this term, thermal. Thermal is for temperature. Also, the temperature is constant. Isochoric is volume. The other meaning of choric is volume. So volume remain constant for this isochoric process. Okay, thank you.